So, my name is V, and I'm going to give you a crash course in hypothesis testing. This is for the Fundamentals in Statistics and Computation for Neuroscientists course at UCSD in the spring of 2016. Alright, so I'm going to talk about some typical hypothesis testing methods, and by the end of the lectures, you should be able to define the statistical model that you're using and some various assumptions that you have to draw when you're calculating these test statistics. Relatedly, you'll have to know when it's appropriate to use each test and why, and you should be able to differentiate an effect size from the actual results of a significance test that you're doing. So I hope you don't find this too boring, because the study shows that 50% of people are actually bored by statistics. But I'm going to try to draw some specific links between your data and the methods that we're going to review today, and outline a general approach for you to think about your data and how to test if it's true or not. So the central question you probably have is, you collected a bunch of data and you have a hypothesis you want to test. So how do you actually do that? You're going to crunch some numbers, presumably, to see if the data you have matches your hypothesis. And given your previous knowledge, your first intuition might be to calculate a p-value. But what test do you choose to do that? Does that depend on a test statistic? Does that depend on a data distribution shape? And actually, what exactly is a p-value? Let's step back for a second and actually think about it and define it. And the place we're going to start is to actually talk about the hypothesis that you're going to test in the first place. So most people start by formulating a null hypothesis in opposition to their real hypothesis, and we're going to denote this with h sub 0 in the rest of the lectures, or just h0. So most of you probably have an idea of what this is, but I'm just going to give you an example with something that you might be familiar with, let's say the firing rate of a neuron. So typically people think of a null hypothesis as a hypothesis of no effect of condition. So that would be true if you just have one group. Here it's just one neuron. And the null hypothesis here is that the stimulus has no effect on the neuron's firing rate. So I'm showing you some data from before the stimulus was presented. So this is just the neuron's spontaneous firing rate. And when this brief stimulus is presented at these times, the neuron seems to increase its firing rate. So the null hypothesis would be that the spontaneous firing is actually the same as the firing during the stimulus itself. Another way to think about the null hypothesis is to test whether a sample comes from a specific population. So the null hypothesis would be that everything comes from the same population. And so I'm going to come back to this example later, but let's say I have some data about the local environment that we all live in. And we also have that same type of data about San Diego, California. And now I want to test, do we live in San Diego or not, given this data? And based on your prior knowledge, you might say, yes, I go to UCSD, so of course I live in San Diego, or near San Diego at least. But we're going to actually try to test this with numbers. And in this case, this is just an illustration that the sample, which is the data about the environment, might come from the same distribution of the data about San Diego. So if we reframe, so that is, the samples are from the same population, or we live in San Diego. And you may think this is kind of trivial, why have to formulate this no effect hypothesis anyway? I'll show you why it's important in just a few slides. So let's go back to our original example of the neural firing rate. Before we framed it in terms of there's no effective condition, but you can also think of it in the same way as comparing the population to the sample that you drew. So reframing it this way, you would think, is the neuron's firing rate during stimulation drawn from the same distribution as their firing rate without stimulation? So that's just another way of reframing your null hypothesis. So how do we test these hypotheses anyway? We've kind of defined what the null hypothesis is. Now how do we test if the null is true or not? in general terms, you can think of this as a probability issue. So you want to know the probability that a given hypothesis is true given some data that you collect. And using the notation that Kathleen and Tom introduced in the previous lectures, I'm going to denote this as P of H given X. And in this case, let's just say the hypothesis is the null hypothesis. How do we go from data distributions to an actual probability? You might have a guess of how this works, but let's show this with a real example. You might think, is that what a p-value describes? Maybe it is. But what a p-value actually is the reverse. A p-value is an estimate of the evidence for a hypothesis by calculating p of x given h, or the probability of the data given a certain hypothesis. And here, we can just substitute h for h naught, the null hypothesis. And this is really a form of inductive reasoning, which is an extrapolation of the data sample you get to a general population. And when you think about it, that's really what people are doing when they're hypothesis testing. But you really have to think carefully to notice that this is not the answer that we're looking for. Like I said, it's the reverse. Because originally we were looking for the probability of the hypothesis given the data, or p of h given x. Whereas a p-value just actually describes p of x given h. So what are the sort of ramifications of this unintuitive way of thinking about p-values? So let's look at an example of how to calculate a p-value from a specific distribution. Let's say this is the probability density function for your null hypothesis. So this should look similar to and familiar to those of you who've watched Tom and Kathleen's lectures. On the y-axis, I'm just showing the probability density. And on the x-axis, we have just a bunch of observations along some dimension. And you know already that the observations at these tails of the distribution, as we call them, are the very unlikely observations. So let's say that we have a specific data point that falls here, right near the rightward tail of the distribution. To calculate a p-value, you simply want to know the probability of this data point if this data point came from this null distribution. So to do that, you look at the area underneath the curve from this data point to the end of one tail of the distribution, and compare that area to the total area underneath the curve. So that's just a proportion. And let's just say that maybe this is about 3% of the area or something like that. That would give you a p-value of 0.03. So Kathleen showed you this slide that tells you that Bayes' theorem gives you the probability of a certain belief given evidence as a function of the probability of the evidence given a certain belief, scaled by your priors and the strength of the evidence. So if you put this in terms of your data and a specific hypothesis, the belief is your hypothesis, and the data is the evidence. So what you want to know is the probability of your belief given the evidence. Here, p of h0 or h naught given x. But you'll notice this is on the left side of the equation. What we really have is actually part of the right side of the equation, which is a description of the probability of the data you have given that you assume some specific hypothesis, like the null hypothesis. So how do you really want to interpret the p-value now that you know that it's just simply describing the probability of the data given a specific hypothesis? The way you interpret this is the way that Ronald Fisher originally articulated how a p-value should be interpreted. He described this through something he called Fisher's disjunction. And I'm simply going to describe the logic of the p-value by showing you what the disjunction is. So, statement 1 is that extreme p-values from a random sample of data are really rare under the null hypothesis. And let's say an extreme p-value has been observed. That is, you find a p-value that suggests that the probability is very low under the null hypothesis. Therefore, you can then conclude that the null hypothesis is false. But you'll notice that that's not quite true. The other possibility is that just a rare event has occurred, and the sample that you got actually does come from the null hypothesis distribution. It's just that it was a very unlikely observation. And that is the disjunction part of this Fisher's disjunction. It's either that the null hypothesis is false or that a rare event has occurred. And it's really important to remember that disjunction has two parts to it. It's not just proving or disproving the null hypothesis, it's also a statement about the probability. That is, it could just be a rare event. So now I'm going to give you a little bit of an example of how we can calculate a p-value from a specific data distribution and apply the logic that we just learned about through Fisher's disjunction to the p-value that we calculate. And really, I'm actually going to tell you how using Fisher's disjunction might get you in trouble. So here's some data that I looked up on the internet. It's the past 10 years of rainfall in San Diego. So this is going back to that example I told you about earlier. There's some data about the local environment, and I'm plotting it here as a histogram. So this is the mean rainfall each month, and on average it's about 0.67 inches per month. And now I have a sample of rainfall from January 2016 in the area that we live in. So where we live, it rained 3.21 inches in January. And now I want to compare if this sample comes from the same distribution of data that I plotted here in dark blue, the data from San Diego itself. This is the null hypothesis, the past 10 years of rainfall, and this is the data we have, or the evidence, the January 2016 rainfall. What we want to do is calculate the probability that this rainfall came from the San Diego distribution. So it's really quite simple. What we have to do is simply compare the area under the curve, like I said, given this data point to the total area under the curve. So we want to compare the probability that this sample was true, this or a more extreme value, compared to the total distribution. So to do that for a discrete data set, all you have to do is count the number of samples that are to one side of the tail of the distribution. In this case, it's anything greater than this value here, x. So any value of this data distribution, italic gray x, greater than or equal to the little x we observe. And that's under the null hypothesis distribution. So you sum all of those, and you divide it by the total number of samples in the null distribution itself. So I have 120 data points, one for each month of 10 years, and I find that only 6 months actually are to the right of this data point. So when you divide that, you get a p-value of 0.05. And if you were to apply only the first part of Fisher's disjunction, you would say, actually, we don't live in San Diego. The null hypothesis should be rejected. But you'll notice that we should not forget the other part of Fisher's disjunction. It's just that a rare event occurred, and it rained a lot in January compared to the average day in San Diego. The p-value that we normally think of as the cutoff for the null hypothesis, or the hypothesis test, is p of 0.05. And that is actually a dangerous way to think about the p-value because, for one, usually people are thinking about it by only applying the first part of Fisher's disjunction and ignoring the fact that the p-value is a statement about the probability of the data. So XKCD parodied this thought by showing how people think about p-values in different ranges. They say really low p-values are highly significant, things right below 0.05 are significant, and when they're exactly 0.05 or a little bit above, you say, oh crap, I gotta redo something. This is just barely at the edge of being publishable. And even beyond that, people start to say, oh, it's very suggestive, it's a marginal effect. And this is actually a problem in the literature. So this is a meta-analysis paper by these two researchers where they looked at all of the p-values reported in a certain journal. I think it was Journal of Experimental Psychology. You can check the references at the end of this video. And what they found is that there's a huge jump when you pass the p.05 magic cutoff. So that's the red bar here. And you see that this distribution is not smooth. Here, it looks like, it's roughly exponential, but then once you jump past the 0.05 cutoff, you suddenly get a huge increase in the number of p-value reports. And really, if we're very honest about all of the studies that we do, there should be no jump in the distribution, and you should really see a more even distribution of p-values all the way up to p equals 1. And this is actually what it looks like in the literature. That XKCD comment was not parodying. In a 2015 paper, these two researchers just plotted the number of abstracts that reported a certain expression by p-value. And I'll show you the top of these. When it's really significant, they call it a paradigm shift. And in some other ranges of p-values around 0.05, they'll say an increasing trend, or results showed that something happened, or that something is novel. And then, right when you get to the edge of significance, we have still a lot of reports. And people say things like it's marginally significant, it's an important finding, or it's little significant, or a strong trend. And at the very bottom of this plot are the unlikely things to report, which is a null effect. So what does it really mean when we get a p-value that's less than 0.05? It does not mean exactly that the null hypothesis is false. And neither does it mean that the posterior belief, or the probability of the hypothesis given the data, is very low or 0. And this is how people usually extend the p-value. And Ronald Fisher wants to also note that it's really about quantifying the amount of evidence towards the hypothesis. It's not that, he says, a scientist allows himself to be deceived once in every 20 experiments. It's really that the test of significance tells him what to ignore, namely all the experiments in which significant results are not obtained. Also, I'm just going to note that this is p of x given h naught is not equivalent to p of h naught at all. And some people think that, if the p-value is less than 0.05, the probability of the null hypothesis is also less than 0.05. Not quite true. And alternatively, you can't flip that around and also say, because you have a low p-value, the alternative hypothesis is really likely, or it's greater than 0.95. Those are not transitive either. So p less than 0.05 is not a probability of h naught being false, and especially not of an alternative hypothesis being true. So how should you actually interpret it? This cutoff is really just a heuristic, which alerts you to rare events under the null hypothesis. So you calculate p of x given h naught, and then you make a bunch of inference, and that depends on the things that you know about your experiment, how you designed your experiment, how sensitive your measurements are, how much noise is there in the measurements you obtain, and so on and so forth. And given the p-value you get, you make an inference about the null hypothesis, or the hypothesis of interest. It does not just strike down as the word of, the statistical gods that this effect is true or not. So then, where did this value that we know of, 0.05, really come from? Some of you may just shrug. Some of you might have heard this value referred to as Pearson's alpha, or the alpha level. But what does that even mean? I'll give you a little bit of a history. So Fisher and Pearson, back in the day, disagreed about how to use statistical measures to interpret your data. And on the one hand, as we saw with the example in the San Diego rainfall data, Fisher wanted people to calculate p-values directly from their data distributions. And he acknowledged this was from a limited sample, but that, he argued, was the only thing you had to go off of. All you have is the evidence that you collect, and you acknowledge that you're making your inference based on a limited sample. On the other hand, Pearson emphasized that every time you do an experiment, there's a likelihood that you're going to make an error, and you're just going to sample, for example, a rare event. And if you think about your data that you collect as just samples from a true distribution, you can just think how often it's true that you're going to get an error. So Pearson wanted people to model their data based on a specific distribution shape before they even did the experiment. They would think about what the distribution was likely to be, and then they set a likelihood of making an error. And the types of errors that Pearson was interested in are described here. These are really the only types of errors you can get. In this matrix here, you see the possible predictions that you make on the top row, and the first column is the true results. So if you predict the correct thing, you'd fall along this diagonal, so you'd get a true positive or a true negative in your hypothesis test. On the other diagonal, you get the types of errors you might get. So a type 1 error is when you predict negative, but it's actually positive. And a type 2 error is when you predict positive, but it's actually negative. So those are conversely called false negatives and false positives. And I'm just going to note that sometimes people often flip these because accepting the null hypothesis often means a negative result. So rather than accepting the null hypothesis being a false positive, they describe it as a false negative. It's really just depending on how you frame the effect relative to a certain hypothesis. So let me just give you an example of why these errors might be insidious and what a lot of people consider the worst error. So let's say you're in a forest and it's really dark and you think you hear a wolf. If you do predict a wolf and there is a real wolf, you will run and you will survive. And if there's no wolf, you predict there's no wolf, you'll relax and go on and do whatever thing you were doing in the forest. And if you predict there's a wolf but there's no wolf, you will think wolf and you'll get scared. But nothing else will happen, really, except you're going to be scared for a little while. But if you predict no wolf and there's a wolf, you're probably going to get eaten. So in this case, your worst result is the false negative. And here, you're thinking that the hypothesis that there's a wolf is true. But here you're thinking that the hypothesis that there's a wolf is false when it's actually true. So you reject the null hypothesis when it's actually true. And that gets you eaten. And a lot of people thought that the type 1 error was something that needed to be avoided more often when you're repeating experiments a lot of times. Because if you're rejecting a true hypothesis, you're going to stop that avenue of research entirely. So really what Pearson said was, what is the acceptable rate of type 1 errors? Let's set that bound and then we'll go from there. So that bound is what Pearson's alpha is. It's the acceptable rate of false negatives. And he recommended 0.05, and you can set it lower, you can set it higher, but this is just a traditional value. 5% error is maybe okay. And conversely, the rate of false positives is called beta. And we'll talk a little bit more about that later. So remember earlier I quoted Ronald Fisher saying that it's not that a scientist allows himself to be deceived once in every 20 experiments. The test's significance only tells him what to ignore, namely all experiments in which significant results are not obtained. Well, what Pearson said was you probably will be deceived once in every 20 experiments. And what you should do is just acknowledge that fact and also set your expectations so that you know 5% of the times you're going to make an error. So I'm going to talk a little bit about how alpha and beta are actually related. So as you know, you want to set alpha independent of the actual experiment that you're doing. So let's say you have a distribution that kind of looks like this. And in your null hypothesis, let's say that the mean is at 100. So if you have a traditional alpha rate of about 0.05, you're going to say that 5% of this distribution is going to get you a false negative. So 95% of the time you're going to get the right result. 5% of the time you're going to get the wrong result. So this denotes the acceptable type 1 error rate. So let's say this is what your alternative hypothesis looks like. Beta is related to alpha because setting your alpha rate also determines your false positive rate. So here, or your type 2 error rate, you have your type 2 error rate. And if you look at the other side of the distribution, now you have power. So this is the amount of time that you will find a significant effect that is true based on the things you know about your null hypothesis distribution, your alternative hypothesis distribution, the effect size you're looking for, and a few different other factors. Power analysis is actually super complicated. So I'm not going to go into a ton of detail about how to do it here. Typically, you simply use a statistical calculator. And we're going to review a little bit about these types of calculations in the next lecture at the very end. So if you have, so let's say alpha equals 0.05 here. If you set your alpha higher, let's say 0.2, you're going to move the boundaries of these lines here. What that also does, you'll notice, is decrease the area that denotes the false positive rate. So you can just drop this line down here. And I'm just going to make up some values for beta here. So let's say beta equals 0.15 here. And here beta equals, oops, different color. Beta is 0.3 or something. So what you'll notice is that as alpha goes up, beta goes down. And conversely, as alpha goes down, beta goes up, right? And you can also think of this as the reverse when you take into account power. So as alpha goes up, your power will go up. As alpha goes down, your power will go down. And as alpha goes down, you're making a more conservative cutoff for your test, right? So typically people will set their alpha as 0.05. Sometimes they'll set it lower, let's say 0.005. And when you're looking at a more conservative test, the false positive rate goes up and your power goes down. So it's always a trade-off. If you're going to have a more conservative test, you probably need to collect more samples, and it's more likely that you're going to see an effect with a conservative alpha if you have a very large effect size. And conversely, if you're going to try to boost your power by making alpha a little bit higher and less conservative, you're also going to get more type 1 errors. So it's always a trade-off between these two values. How do you actually select an alpha level? You can change it. It doesn't need to be 0.05. And actually standards differ for different fields. You might have heard in physics the idea of 5 sigma, so that would be 5 standard deviations away from the mean. This is a really low alpha because they're making their test very, very rigorous. They're saying that they need a lot of evidence in order to reject the null hypothesis. And that's actually 0.000003. I think I said the right number of O's. Versus in biology or psychology, the level is often 0.05 because 5% is an acceptable rate of error for somewhat messier sciences. So when you select an alpha level, you should factor in a bunch of things. You should factor in the likelihood that there's some error that you haven't accounted for that's introduced into the sample that's not really clear from the data distribution. You should also think about the consequences of either a type 1 error or a type 2 error. So remember that if you're going to institute a lower alpha level, you're also going to get a higher beta level. So you might accept the null hypothesis when you should actually reject it. And that just makes your test more rigorous, but maybe sometimes, that's not such an ideal thing. And you might want to also think about the consequences of actually accepting your null hypothesis when you should really reject it. So here's an example of how you might apply this p-value logic in the wrong way. And then on the 21st test of the color and the 22nd test of jelly beans and acne, they get a positive result. That is, they reject the null hypothesis, and they say green jelly beans are linked to acne. But you'll notice that this is in the tail of the distribution. If you look at all of the data across all of these studies, this one is the outlier. And it happened because there was a really rare event, and their sample was probably not random. So I've outlined all these problems with thinking about p-values as the probability that your hypothesis is true or not, and whether you should accept or reject the alternative hypothesis, but that doesn't really tell you what you're supposed to do with your data exactly. So let's go back to our original question. You collected a bunch of data, and you want to do something. Now what? Okay, so I'm about to outline the common approach that people take to hypothesis testing. But I'm just going to note it's probably not the best way most of the time. It's still important to know the steps that people take and the logic that they're going through in their head when they're going through this hypothesis testing. And indeed, some of the time, this is a perfectly fine method to use. So let's review. The most common approaches actually blend the methodologies of both Pearson and Fisher. And you already see that sort of in your daily paper reading, that people often say p of 0.05 is the cutoff, even though p-values aren't totally related to type 1 errors in the way that people think. So usually people define some hypotheses. They'll define a null hypothesis and probably at least one alternative. And the format of that hypothesis will fall into some assumptions of some family of statistical models. And I'll go over those in a couple of slides. And Vlad, in the next lecture, will review a bunch more different statistical models and tests. Then people will examine their data, they'll probably plot it, they'll maybe look at the distribution, and they'll say my measurements are continuous or categorical, or define a bunch of things about it. Then they'll choose a test based on number 1 and 2. And they'll probably check to see if their data roughly meets the assumptions of the test they chose, and if not, they'd choose another test. And then they calculate a p-value based on that test. Now, you should also do these things. And people are not always going to do these following things, but it's important to think about. So you should actually be designing your experiment with a testable null in mind. And when you have that null in mind, you should have the appropriate test already selected so that you can design your experiment with the appropriate parameters to actually fit the test. Then you can check to see if the sample you're going to draw has enough power to draw the conclusion that you want. And this involves a little bit of guesswork, but you can completely concede in your discussion or your methods when your sample might be a little too small or underpowered, and just admit that that's true because everybody knows that's part of the scientific process. Additionally, you should be reporting all the relevant parameters of your statistical test. So this includes degrees of freedom and the type of test statistic, the exact value of the test statistic, and the exact value of your p. So, for example, that means saying p of 0.023, not just that p is less than 0.05. And that's because it's really important so that other people, such as reviewers or just readers, can just make a judgment about the data that you presented for themselves. So you should recognize that when you're doing a hypothesis test, you're essentially just presenting an argument to some people about the data that you collect. And your argument depends on statistics a little bit, and you outline all the statistics you did and how you got them, and you say, I think this is correct. Someone else should be able to go back through your data and run the same test or a different test that they think is better and calculate their own statistics for it. So you should really aim to have reproducible statistics and transparency in the statistics that you report. And then finally, it actually is important to also report things such as effect size, even just the mean of your effect, and let's say the confidence interval of your sample itself. And these are all important because if you have a really high, significant p-value, really low p-value, you might have a tiny effect size. Let's say it's a very reliable effect, but it really is so tiny it almost doesn't matter. That's something that should factor into your discussion, and you should be able to recognize that it's consistent, but it may not have a huge impact, and maybe not as large of an impact as you originally thought. So before we go on to the more pragmatic section of this lecture, let's define a few terms. I've been talking a lot about test statistics. What actually is a test statistic? Test statistics are something that you calculate based on a specific distribution of data that you get from your sample. And you might have heard of some of these test statistics before. There's a t-value, an f-score, and a z-score, for example. And these are all calculated often based on descriptive measures of that distribution, such as mean or standard deviation. Now, the value of the test statistic is then compared to a theoretical distribution of that same statistic, and those things are referred to as the t-distribution or the f-distribution. These distributions are derived based on some assumptions about the null hypothesis. And if you're really interested in how these distributions are derived, Wikipedia is a great resource. The derivations are great, but they're a little bit outside the scope of this lecture. So, for example, you might have a normal distribution, and you can calculate the t-statistics for all of that normal distribution, and then you generate the t-distribution. Or you might have a binomial distribution, and you're going to calculate some statistic based on all different values of the binomial distribution. And these are different depending on what type of variable you have. So you might have a continuous variable or a discrete variable. And they also might vary depending on how your samples are collected. So a lot of these distribution derivations depend on the idea that you're taking independent samples. And there are a bunch of other caveats, and this is often where the assumptions about the test that you're doing come from. You're comparing your test statistic to a specific distribution, which is based on a lot of different assumptions. And those are the assumptions that you need to be thinking about when you decide to calculate a test statistic and run a hypothesis test. So from here, you can actually calculate the p-value of the test statistic. So you'll notice that the general interpretation of the p-value is a little bit different. So you're comparing the test statistic to the rest of the test distribution. So the p-value you generate is the likelihood that you're going to get this test statistic under the assumption of the null hypothesis of the general T or F distribution that you're looking at. So that's not quite the same as the p-value that we calculated earlier, which is the probability of your evidence itself given the null hypothesis distribution of your data. Here the null hypothesis distribution is the T distribution or the F distribution. Here's some other basic terms and notation. If you're unfamiliar with these terms, I suggest pausing the video and reading through these definitions. The one I'm going to highlight here is the difference between a parametric and a non-parametric test. So I just described how some test statistic distributions are based on assumptions. A non-parametric test is a test that does not assume the samples follow a particular distribution. People often refer to these as distribution-free tests. A parametric test, on the other hand, assumes that the sample data comes from a particular distribution, such as the normal or Gaussian distribution, or binomial, or so forth. And the other terms that you should be somewhat familiar with based on previous lectures are the standard error of the mean, a confidence interval, or a sample mean, which is denoted by mu. And I'm going to be talking a little bit about degrees of freedom, but we will go into more detail on this in later lectures. Simply, you should think of it as the number of observations that you have minus the number of necessary relations among these observations. And it's not super important for you to know exactly how this changes the distributions that you're looking at, but you should always check to see how to calculate the degrees of freedom for the test you're doing. So we're going to be focusing on the one sample t-test, which is a parametric test, for the rest of this lecture. It's basically the most simple parametric hypothesis test you can conduct. And in the next lecture, we're going to review all of the other types of simple hypothesis tests that you might encounter. And we'll list a bunch of other ones, but essentially that'll cover the theoretical basics that you need to know about how hypothesis tests are conducted. So here's the t-distribution on the left, and you can see that it varies for these values v, which are the degrees of freedom. So as the number of samples goes up, the degrees of freedom go up, and the shape of this distribution changes slightly. And as I said before, you're going to calculate the test statistic and then compare it to this distribution on the left. So here's the actual formula for that. The t-statistic is equal to the sample mean minus the value that you're testing against, which is the mean of the null hypothesis, divided by the sample standard deviation, which is also then divided by the square root of the number of samples. And if you'll remember before in Tom's lecture, we reviewed what a sample standard deviation actually is. It's a metric of the distance of each sample's point to the mean, normalized by the amount of samples that you have. So the t-statistic is then essentially just the distance between the mean of your data and the expected mean in the null hypothesis, then scaled by the variation in the points of your sample. This is a little bit of a simplification, but that's how you can think about this formula up on the upper left. So can we use a one sample t-test for that example that I showed earlier? This is that distribution of rainfall data and the local rainfall for 1 month in the place that we live in. If we try to actually calculate this test statistic, we'll find that the sample standard deviation is 0 because we only have one data point from 1 month. Furthermore, you can already see that this is not a normal distribution, and a t-statistic always depends on the assumption that your distribution of your data is normal, and this is clearly not normal. So this is not the right model, and we'll come back to this example later and show the actual correct model for looking at this data. So let's actually try an example with an actually normally distributed distribution. So IQ scores are actually forced to be normally distributed, and you'll see the average IQ distribution on the bottom, and it has a mean of about 100 and the standard deviation of about 15, and the scores have been formulated to follow a normal distribution. Now, the sample that we have is 30 students, and we find that their mean IQ is about 104.3 with a standard deviation of 11.6. So we want to know whether these students have an IQ that is significantly different from the mean IQ. And I'm just going to go into a little bit of a sidetrack about why IQ scores can be normally distributed in this way. It's probably through a process called z-scoring. So you might have heard of this before. Z-score is a way of making your distribution have the properties of a normal distribution. So what you do to calculate a z-score is that you take the value of whatever data point you have, so you do this for every single data point that you have, and then you subtract off the sample mean and divide by the sample standard deviation. What this will do is give you a mean of 0 of the z-scores and a standard deviation of 1. So you can see here on the right is the z-score distribution. The mean is always 0 and the standard deviation is always 1. That's denoted by the sigma signal here. And since the standard deviation and the mean are standardized, you can calculate a bunch of different measures based on the z-score. For example, the percentiles are very clear when you have a z-score distribution. For example, 2 standard deviations away, you're going to get a 2.14 percentile little chunk before you get to the next standard deviation. So many scores of tests are based on z-scoring because you want to normalize so that you get a mean that is equal to the mean of your entire population, and then the scores are relative to that mean. So SAT scores, ACT scores, and IQ are all z-scored and forced to be normally distributed in this way. Now let's go back to our example. All we have to do is calculate the t-statistic down here based on the formula that I gave you earlier. So now we plug in the sample mean, the null hypothesis mean, the sample standard deviation, and the number of students that we have, which is here 30. And when we do all this math, we get a t-score of 2.03. So now what do? We compare this t-score to the distribution of t-values for the correct number of degrees of freedom. So here is that distribution. So the degrees of freedom here is 29 because we have 30 students and we're making a single comparison. So that's 30 minus 1, which gives you 29. And your degrees of freedom, as I said earlier, will differ depending on the test that you're doing and the number of groups or samples that you have. The distribution of your test statistics also varies with the degrees of freedom. So here I've just selected out the t-distribution for a value of 29 degrees of freedom, and here's our test statistic, which is 2.03. We want to know how extreme this test statistic is based on this distribution. So basically, we just find the number of samples that would be in this tail of the distribution and compare it to the rest of the area under the curve here. And this is just a one-tailed t-test because we're just looking at the right tail of the distribution, comparing it to the entire left side of the distribution. So when we do the one-tailed test, the p-value is 0.026. But a lot of people recommend just defaulting to a two-tailed test. And this is usually what you should do unless you have a specific idea of which way your effect should go. So it could have been the case that the students had a lower IQ or a higher IQ than average. So it's appropriate to use a two-tailed test and to see whether the t-statistic is either on the right tail or the left tail of extreme. All you have to do is simply multiply your p-value by 2 in order to find the proportion of the tail area to the rest of the distribution. So before, our value was 0.026, and now when you multiply it by 2 to get the two-tailed p-value, it's 0.051. So I've referred to effect size a few different times here. And basically, this is important because you just want to know how large the effect you're reporting is. And this will vary depending on the number of samples that you have, the standard deviation of those samples, and a few other variables. So actually, the measures for effect size typically vary from test to test. For the t-test here, you can calculate what's known as Cohen's d. You might come across this if you read a few different papers where they often use t-tests. So, just to remind you, this is the t-test formula, and this is the formula for Cohen's d. It looks very similar, you'll note, because you're still using the sample mean and subtracting off the null hypothesis mean and dividing by the standard deviation. But you do not normalize by the subject number. And when we calculate the actual Cohen's d value for our sample, we get an effect size of 0.37. This is a pretty small effect size, but we have a somewhat large t-value. This is because the t-value takes into account how many samples we have, and since the standard deviation of our samples are pretty low, this boosts the power of our test. So even though we have a small effect size, we have a large t because we have plenty of samples to confirm that the tiny effect size is actually present. And as I said earlier, there are multiple effect size measures that you can use depending on the test. There's even a different one for the t-test that I'm not covering here. So look those up as necessary to report your effect sizes in your papers. Now, I've also talked a little bit about confidence intervals. You probably know what these are, but they're a descriptive statistic describing the minimum and maximum value bounds for a large percentage of your data. So typically, people report 95% or 99% confidence intervals. And all that means is that 95% of your data falls within these bounds. If you assume a normal distribution of your data, you can actually calculate the confidence intervals with a simple formula based on your mean and standard deviation. So, if you have a distribution that looks like this, for example, you can easily tell the percentiles because the distribution is symmetric, has the same standard deviation on both sides, and centered about a central mean. But in practice, this won't work really well if you have a non-normal distribution or any outliers to your even otherwise normal distribution, because 95% of your data will probably lie within that formula, but there might be a couple data points that fall slightly outside of that. So we'll cover this more in the problem set where I'll ask you to calculate confidence intervals for a specific sample. And in practice, you won't actually need to do any math to actually calculate your test statistics or to find your p-value. This is because people have built so many different statistics packages in many different programming languages, and these all have these formulas built in already, especially for the typical parametric tests that you use. The ones I'm listing here, which are probably one of the ones that you're going to use, also will have the non-parametric formulas for most of the tests that you're interested in. Now, as a neuroscientist who's collecting data, you're essentially just being an applied statistician, and your job is not to know the formulas in and out, it's to design your experiments in a sensible way with foresight into how statistics will address the questions that you want to answer. You need to think very carefully about designing your experiment such that you can calculate the appropriate test statistic at a power that will reveal the effect size that you desire. Then you can choose the right tests to interpret your results in a sensible way. And often this will involve referring to previous literature to know the size of the effect that other people have reported and the number of samples they needed in order to find that effect. But it'll depend on the specific question that you're interested in. Finally, you might be able to z-score your data if you know that it's fairly normal. And from the central limit theorem that Tom covered in his earlier lecture, samples will tend towards normality if you have a lot of data points. Then if you have a roughly normal sample, you can z-score your distribution to get a familiar shape that looks something like this. And a p-value can always be calculated from a z-score because it's forced to be normally distributed. Here's an example of that here. Let's say we have a new student and we want to know if their IQ is unusual based on the student IQ population that we collected before. So now we're going to z-score our student IQ population because we want to force it to be the normal population that we're comparing the new student to. So we calculate the z-scores based on the formula I gave you earlier, and you do that for every single sample. So this is what the z-scored sample looks like. It's slightly skewed, but we're just going to say this is approximately normal given the distribution of data points we had earlier. And now the new student has an IQ of 107. So we calculate the z-score for the new data point, and then we see how far the z-score is from the mean. Now, from what we know about the z-score, one standard deviation is equal to 1. So this is less than one standard deviation away from the mean. Probably this student doesn't have a really unusual IQ. So to calculate the p-value itself, you compare the z-score to the rest of the distribution, and I've done the calculations here for both the one-tailed and two-tailed tests. The p-values are pretty high. So like I said earlier, this student probably fits right within the normal range of this distribution of students. What if you have a weird distribution? Maybe it's not normal, like the rainfall example I showed you earlier, or maybe you have a bunch of outliers or some skew to your normal looking distribution. Like I mentioned earlier, there are non-parametric versions of all of these tests, but they're often less powerful because they'll require a little more data or a little less noise. But the trade-off is that they'll handle these non-normalities much better than the parametric tests. So we're going to review those in the next lecture. Another way to deal with weird distributions of data is to just use bootstrapping and permutation tests. This will come in a lecture in a couple of weeks, but just know that if you have a weird distribution which isn't modelable by any statistical model, and the non-parametric versions may be a little too underpowered to find the small effect that you're looking for, you have another option, and we'll review those in a couple of weeks. So thanks for watching this video. Here's some references to the figures and quotes that I had earlier in the paper.